The EM algorithm for Gaussian mixture looks very much like the k-means algorithm. In the EM algorithm, our gamma i's are probabilities between 0 and 1, but in the k-means algorithm, gamma i's are either 1 or 0, meaning each observation will be allocated only to one component, one cluster, which is the one it is closest to. A natural question would be, under what scenario the EM algorithm will sort of converge to or behaves like a k-means algorithm, or equivalently, let's look at under what kind of scenario our gamma i's will be close to 1 or 0. To answer that question, let's look at the ratio of gamma I divided by 1 minus gamma I. And you can pause the video and you can think about what the ratio will look like. And it would be pi, 1 minus pi, the ratio of the prior probabilities, and then the density function of the first component and versus the density function of the second component. Now, to simplify our discussion, I'm going to assume my thetas, my sigma square are the same. Okay, and then you can rewrite this ratio as something like e to the power minus 1 over sigma square, and then xi minus mu1 square minus xi minus mu2 square. Okay, and then consider the scenario where my sigma square is very, very small, close to 1, which means my 1 over sigma square is very large. Then you can see that if xi is just slightly closer to mu1, then what's inside the bracket will be a negative number, and then times another negative big number, and then we'll find out that this ratio gamma I over 1 minus gamma I is going to be very large, which means gamma I will be close to 1. And similarly, you're going to find out if xi is slightly closer to mu2, then you're going to find out, and you can do the argument, and you're going to find out gamma I will be very close to 0. So the k-means algorithm essentially can be viewed as a limiting behavior of the EM algorithm with Gaussian mixture with the error variance being 0.